I'll anyway start. So in the last class we had started sectional forces in beams or members. And what we said was that suppose there's a beam, I show this as a general loading, or another beam like this. This is a fixed end in the wall, and on this we show some distribution of forces, moments like this. So we have a force F1, there's a distributed force F, and there's a moment M, or let us say in this one we have a distributed force F, there's a force F2, a force F3, and so on. So if these are the this is the general loading on the beam, then in sectional forces what we try to find out is that given this beam, if I make a cut at any section, say XX or YY, then in the cut section, so if I now draw the free body diagram of the cut section, this is point A, I will get AY, I will get AX, and then in the cut section which I have made, so this is the cut section which have been made at section XX. What are the forces? And what we showed was that a force which is transverse to the beam in the direction perpendicular to the axis of the beam, this force is what we term as the shear force. And a moment which is in the direction perpendicular, so shear force, the direction is perpendicular to the axis of the beam, and similarly a moment in a direction perpendicular to the axis of the beam, this is what we termed as a bending moment. So these were the two things which we first talked about. We defined a shear force and a bending moment, and after that we talked of a sign convention. And the sign convention was done in such a way so that whether you take the left section or the right section, the shear force is given by a unique value. So therefore what the sign convention which we are following is that if you cut, if x-axis is like this, then this shear force V is positive, and if you cut a section from the left side, from the other side, then this V pointing upwards is positive. So this is the sign convention which we are following. Some books, as I told you, follow a reverse convention, but all my this thing will assume that this is the sign convention we are following for V. For bending moment, the convention is normally more uniform. It's the same, that on a section where the outside axis is pointing in the positive x direction, a counterclockwise moment M, this is considered as positive, and on this section a clockwise moment, so counterclockwise M is positive, and in this one a clockwise M is considered as positive on the right end, and this is on the left end. So this is the sign convention which we have followed, which I discussed in detail in the last class. Next then we said that we will be talking of shear force and bending moment diagrams. Now then the basic question comes, how do we find shear force and bending moment? First we will talk at a given section XX, And the answer to that is very clear. We do it by equations of equilibrium. So here you'll have to look at the particular problem in question, but otherwise in general what you have to do is first you draw free body diagram of the full beam and find reactions at the supports. Now it turns out in some of the problems this may not be needed. These reactions will come out automatically in case everything happens to be at one end. All the unknowns are at one end, then you start from the other end and then you just keep on working without finding reactions at supports. But in general we'll first find the reaction at supports, and second part will be we draw the free body diagram of the cut section of the beam where section XX is exposed, and on this section XX, because it is exposed, we will have V and M as unknown forces and moments. At this section XX, which is exposed, we will have shear force V and a bending moment M, which will be unknown. The directions of these will be drawn as per sign convention, and then our answer will be either positive or negative. So this is how, and then after that we regions of equilibrium for this cut section and get the answers for V and M. So for example, for the beam which I showed, which I flashed here, and let's look at this. If we have to find shear force and bending moment at section XX for the first beam, so what I'm going to do is let me just keep this as it is, and let's try to, I'll not solve the problem in sense of with numbers etc, but just tell you. So first we draw free body diagram of the full beam. So we have, let's call this end as B, we have end AB. Now at end A we will have RAY, RAX. At end B we will just have BY. There is no RBX. So we call it BY or RBY, whatever it is. And then when we draw the full free body diagram, either I can show this equivalent, this force as it is, this small f which is force per unit length, or we can draw its equivalent with correct line of action. So this force F, either I will show it like this or I will replace it with a point force, and in this case it will act at half of the length over which this F is acting, because this is a uniform force. And then I will show the moment M, I will show the force F1. And on this free body diagram, as I told you, I won't solve the full problem. So first I will do sigma Fx is equal to 0, sigma Fy is equal to 0, sum of moments is equal to 0, and this will give me Rax, Ray and By. So when I solve this, I will get these answers. Now this is not the aim of my solution. My solution says that I have to find shear force and bending moment at the section XX. But for that you will realize I need to know the reactions at A or the reactions at B. So now I don't need to know both. So if you look at the problem, either I will find reactions at A or the reactions at B. I don't need to find both. Let us say I use the reactions at A. So then what I will do is, as step 2, I draw free body diagram of the cut section. So now when I draw the free body diagram of the cut section, I will have Ray, Rax. These are no more unknowns. I know these values. And in the cut section, I have this force F, but now this is acting only for some length x1, not L, because overall length was L, but now it is acting only on a small section depending on where the cut is made. And then on this cut, I will show, because this is a left hand cut, I will show a force V and I will show a bending moment M. So these are what will come in when in the free body diagram of the cut section. And now when I do sigma Fy is equal to 0, this will give me the value of V. And when I take sum of moments about A is equal to 0, or I can take moments about X is equal to 0, I can take moments about any point, I will get the value of M. One mistake people tend to make. If I take moments about A is equal to 0, then obviously Rax and Ray will not come into picture. But then keep in mind, there is this force V which is there in the free body diagram. So the moment due to V cannot be forgotten. So if you are taking moments about A is equal to 0, you don't take the moments only because of this section of the force small f. In addition to that, you also have to take moments about of force V about point A. Or the other thing is you can take moments about X is equal to 0. If I take moments about X is equal to 0, I will get moments because of Ray and the moments because of the cut section, and then I don't have to bother about V. Both the ways will give me the same answer. Or in addition to this, another student, instead of this, we could also have taken FBD of the right section. Now what you will notice is, if I take FBD of the right section, that means I am starting from B and I am coming to X. Now this is my original figure. I am starting from B, I am coming to X. So now when I draw the free body diagram of this cut section, what I will get will be a By, I will get F1, I will get this moment M, and I will get this force F which is acting on this for a length of L minus small x1. So now in this, when I draw the free body diagram of this section, I will show shear force V in the opposite direction and I will show the moment M as clockwise. And now when I do sigma Fy is equal to 0 and sum of moments about B is equal to 0 or moments about X is equal to 0, these will give me the value of V and M. So either I use this or I use that. I use one of these two things and get my answers, shear force and bending moment. Now notice, when I draw the free body diagram of the left part, so when I am drawing the free body diagram of the left part, I don't have to, let me call, sorry, I should call this moment as M1 because to differentiate it from the bending moment M. Now when I draw the free body diagram of this left part, I don't bother about M1 and F1. I don't care about these because they are not in my cut section. Does it mean that they are not affecting the shear force and bending moment at all? They have to affect. And how do they affect? Will somebody tell me? Okay. So now let me try to interact. Some college, just random, please pick up one college where the video is working. No. See Pune always. Why? Please take something else. So we have to have some more colleges. Otherwise, we'll go back to CE Pune. I have nothing against CE Pune, but it's just that I've been interacting only with CE Pune always. Yes, okay. OXCE. I would like somebody to answer the question which I'm posing. I'll pose the question again. And maybe other colleges, please listen to this. So, who will come and answer my question? My question is this. Who is answering? Is there somebody ready to answer? Otherwise, we move to some other center. I just don't know. Maybe some center, whoever wants to answer the question, please inform us. I would like to interact. Otherwise, I think these lectures are of no meaning. If I just have a one-way delivery, I could easily send a video recorded cassette of my lectures. So somebody who would like to answer questions, 2 or 3 of those groups, please inform us, and then wherever I feel I will take a break, I'll ask you so that this can be a more productive exercise. Please inform us, otherwise I'll continue with my lectures, and if that is how you want, then this will be just like a one drab set of video recorded lectures. I can continue like this. But actually we are not making full use of the technology and the platform which has been provided to us. So I would still please request you to interact so that we can understand. Okay. Now, the question which I was raising was this. So since nobody is interesting, I will raise the question, I will answer, and after that I will move on like a robot, just keep on delivering lectures like that. That is what you seem to want. Is that right? Please send some comments. It's really very frustrating. You seem to be, I'm supposed to be talking to a live audience, not to a dead audience. Still no reaction from anyone. How many colleges? There are about 26 colleges. Yeah, okay. Is no, that's my own sign. 26 colleges are there. Not even a single college wants to interact, wants to talk, give some feedback. Okay, even if you're not understanding, then I should know that you're not understanding anything, so that I can make it simpler if it is too simple. Or if you're understanding, at least it gives me a positive feedback. I feel like teaching better, it gives me a good feeling. But speaking to an audience which is not responding at all is a very bad feeling, please. Okay. Because I'll ask questions, and sometimes the answers to these questions when you give or when I answer really brings the insight out. Otherwise, if I just keep on talking and talking and talking, there is no point. I don't even know whether you want to listen to this or not. You are being forced to sit there by your teachers, so that is why you are sitting there. Okay, so my question was this. I'll repeat this. I draw the free body diagram of the left section of the beam. I find RAX and RAY. I find the shear force and bending moment. Now in this, M1 and F1 have not come at all. So that means if I change the value of M1 and F1, will this shear force B and the bending moment M change or not? And if it changes, then where does it show up in this free body diagram? Yes, I'll spend another 1 minute. Anyone who has the answer to this. If you have not understood the question, still try to communicate to me, tell me that you have not understood the question. See, Pune, try kar lijiye, if that is the one which responds only. That seems to be the only college which responds. So let's try with at least, I have one college where. Yeah, so my question was, if I change the value of M1 and F1 here, will the values of shear force and bending moment change or not? Can anyone tell me, please? At least you are good enough to come on screen. Most other colleges will not even come on screen. They have just shut down the two-way video. Any response? Yes. Hello. Yeah. Is the mic working, ma'am?
Yes.
Yeah. So my question was, if M1 and F1 change, will the shear force and bending moment change or not?
Yes, sir. It will change because
So then,
there
but then we don't have M1 and F1. Yeah. What was the reason? Please tell.
because we are considering the free body diagram of that beam, then RX and RAY are also get changed.
They will change. That's right. That's the correct answer. Because if M1 and F1 change, then RAX and RAY will change. So the effect of M1 and F1 in the entire beam is coming on through the support reactions. So if M1 and F1 change, RAX and RAY will change, and that is how we will get the effect of that in V and M at a section, even if it does not include M1 and F1. Thank you. That was a good answer. You answered correctly. Thank you very much. Thanks. Okay. So now let us move to, now this was finding shear force and bending moment at one section. Now the next thing which I told you is that often we are interested in drawing what are called the shear force diagram, and the bending moment diagram. And what do we in these diagrams? We plot V versus X and M versus X, where X is the distance along the beam. One question, okay, good. There's a question from OXE. Yes, sir.
My question is that how, since F1 will influence the normal reaction RAY and RAX, but how will M1 influence that part, RX and RAY?
How does M? See, your question is how does M1 affect RAX and RAY? Is that the question? Yes, okay. See now, if I take, see what do I get for sigma Fy is equal to 0? I will get RAY. Let me take a simple situation. Okay, it's a very good question, and the question which it looks to me is that suppose if I have a beam like this is RAX, RAY, this is BY. I'm simplifying the situation. I'm putting a single force F1 like this, and I'm putting a moment M1 here. Now your question is, how does M1 affect the value of, so this is Y, this is X. How does M1 affect RAY? Now when I do sigma Fy is equal to 0, what I will get is RAY plus, let's call it RBY only, RBY is equal to F1. Now when I take moments about A is equal to 0, this will give me F1 multiplied by L1 minus M1 minus RBY times L is equal to 0. So therefore, the value of RBY depends on M1. Whether M1 is 0 or not, that will determine the value of RBY. But so there, and similarly, if RBY is affected, RAY will be affected. But I think you have a very valid point. It will not, as per these equations go, the value of RAY and RBY will not depend on the position of M1. Whether M1 is applied at a point A or it is applied at a point B or applied at a point C, it will not make a difference. But then, where M1 is applied, whether it is A or B or C, the difference will come when we draw the bending moment diagram, and that will come soon. Does that answer your query? Maybe let's go back to them. Does it answer your query? Okay.
And that means RAX and RAY RAY won't depend on M1. It is just RBY which depends on M1, right?
Pardon?
That means RAX and RAY won't depend on M1. It is just RBY which is dependent on M1 as per the given problem.
No, no, RBY, once RBY is changed, then RAY will also change.
Oh, I get it. I'm sorry. Thank you.
Okay. So it's not just RBY. Okay. There's something from CE Pune. Could you please correct me quickly to CE Pune? Let's get to their query. Thank you very much. Is
Hello, sir. I have one question.
yes,
Um,
yes.
Why we have not considered the moment in the left section of that beam? Because moment is a free vector, so we can move it along overall beam.
No, see, that's what I'm saying. That the point where this moment acts, that will become impossible. See, it is a free vector, it can be moved along. But these free vector concepts we have to use very carefully. They are free vector as long as we talk of a full rigid body. But when we talk of sectional forces on beams, then we have to look at a particular section only. And then the free vector, if it is not falling on this, it will not act on this part of the body. So the free vector concept is correct as long as we talk of a full body. So now, as long as I'm talking of this full beam, doesn't matter where M1 acts. It's a free vector. But once I'm making a section here, I make a section at a particular part of the beam, then I have to, the free vector, if moment is not here, it is not here. Okay, there's a connection problem.
Okay.
So where is my voice going? Okay, the screen here is not going, so I'll continue interacting with this. Is your answer, is your question answered?
Yes, sir.
Okay, what's your name?
Mrinali Mani.
Okay. Are you finding the lectures useful?
Yes, sir.
Thank you. Okay, I think that in a minute we'll get back to the written part where I think there seems to be a technical problem. We should put a slide saying रुकावट के लिए खेद है or something like that, which Doordarshan puts. So I'll, but anyway, my picture is going there or no? Audio is going. Okay. So I believe the video is not going. Is that true? Okay, अभी आ जाएगा, आ जाएगा. Meanwhile, maybe if somebody else wants to ask something, if something is not clear, please feel free. So maybe somebody can sing a song from side and till the video comes, maybe somebody can sing a song or something like that. Okay. So now let's see. Okay, let's continue. Let the video come. I think I can talk with the audio. If the audio is going to, well, as I told you, we are next topic now. What we are looking in this topic next will be shear force diagram and bending moment diagram. And there, what we do is we make a graph of shear force as a function of distance along the beam and bending moment as a function of distance along the beam. I am not using axial force. Actually, there is something called an axial force diagram also. So we can draw an axial force diagram also, but generally these are the two things which are important. So that is why we talk of shear force and bending moment diagrams. So what we will learn is, and what you will see is, to draw shear force and bending moment diagrams, you don't need to write the equations of equilibrium again and again. I will tell you some general rules with which you see the loading on the beam, and just by looking at the loading on the beam, you will be able to directly after that draw the shear force and bending moment diagram. Maybe you need to draw the overall free body diagram to find the reaction at the ends. But after that, you don't really, is this going now? Is the writing part going? ये जा रहा है? And my video? Is this going? Thank you. Is this going now? Thank you. Great. Thanks. So hopefully my face will also come to you after some time. So let's see anyway. Even if my face doesn't come, it's not important. This part is more important. Okay. So now let us see some simple rules for drawing shear force diagram and bending moment diagram. What we do is we start from the left end. Let us start from the left end of the beam. Now what we see is, let us say this is our cut section. Now what I am trying to tell you is, what is the effect of a point force P, a single concentrated force P which is acting downwards, what effect it has on V. And what you see is that if I do a sigma Fy is equal to 0, I will get P plus V is equal to 0. So I will get the effect of V will be minus P. So therefore what I get to my rule number 1, a downward force P induces on all sections to its right a shear force V is equal to minus P. So you start from one end. If there is a downward force P, for each of such force to the shear force you have to add minus P. And similarly from here it will be clear, an upward force P on the beam induces on all sections to its right a shear force V is equal to plus P. This is following our sign convention which is being used in Beer and Johnson. If you use the sign convention in Crandall and Dahl, then the results will be with opposite signs. Nothing else will change. So this is the effect of a point force P on all sections to its right to the shear force. Okay. Next, let us see the effect on the bending moment. So we had a force P, this was the cut section, and let this distance between the distance from cut section to the point of action of P is equal to zeta. So now what we have seen is there is a shear force V, there is a bending moment M. Okay. Now when if I take moments about x is equal to 0, then what will I get? If I take moments about x is equal to 0, then what I will get is the moment because of, so I will get moment plus P times zeta is equal to 0. So that means because of P, the amount of moment which I get will be equal to minus P zeta. So what I can generally say as, and this gives me rule number 3, a downward force P induces on all sections to its right a bending moment m is equal to minus p times zeta, zeta being the distance from the cut section. See, this is not the distance from the origin. This is the distance from the cut section to the point where P is acting. So this is what I get for the bending moment, and just copy this down, and then I will make the fourth rule which will be exactly identical. I will replace the downward by upward, and the moment you will see will become m is equal to plus p zeta. So this is just the sign change in the fourth rule. So when I put the fourth rule, which is actually nothing but a repeat of this, that an upward force P induces on all sections to its right a bending moment m is equal to plus p zeta, and once again zeta being the distance between the cut section to the point where P is acting. So this is what a point force does. So that means if we have a force P which is acting, and if this is the section, so this force P has two effects. One is in the shear force, this causes an effect of minus P, and in the bending moment it causes an effect of minus P zeta. The effect of the first thing will be seen in the shear force diagram, effect of the second thing will be seen in the bending moment diagram. Now we also have a third thing, and this is the third thing in terms of notion, but in terms of formula this will become the fifth thing. What happens if there is a moment m1 which is acting? What is the effect of a concentrated moment m1 on all sections to the right? On all sections after we cross, what is the effect of moment m1? So now we have V and we have M. Now first what we see is it has no effect, and I will use the term explicit effect, on V. In the shear force diagram, the presence of a concentrated movement will not make any difference at that point locally. Overall it will have an effect because the reactions will change because of M1 or whether M1 is not there. But otherwise, in terms when you are drawing the diagram, at that point there will be no effect on V. And if we do a moment balance, then what we get is M plus M1 is equal to 0. That means M1 or M is equal to minus M1. So seeing this, we can write our fifth rule. The fifth rule says a counterclockwise couple M1 induces on all sections to its right a bending moment M, which is equal to minus M1. And from here the next rule, which is just opposite of this, a clockwise couple M1 induces on all sections to its right, a bending moment M is equal to plus M1. So if we know these rules, then as I will show you, I'll take up a very simple example today. We can draw the shear force and bending moment diagrams by without writing equations of equilibrium except for the support reactions. So let us see how to apply these rules, and these rules are coming from, they are not coming from some magic, they are coming from equations of equilibrium. So let's now try to solve a problem. I'll take a simple problem where we have point forces. So there's a beam, this distance is 2 meters, this is 2 meters, this is also 2 meters. I'll just make it, I have a graph paper. So this distance is 2, this is also 2, and this distance is 2. So this is the total beam. Now here let's call this end as A, which is free. At end B there's a pin joint, and at in the middle C we have a force F which is 40 kilonewtons, and at D we have a roller. So ABCD is an overhang beam as shown, and at end A also we have a force 20 kilonewtons loaded as shown. So on A there's a 20 kilonewton force, on B we have a simple pin joint, on C there's a 40 kilonewton force, and D there's a roller support. And our question is, draw shear force diagram for the beam. Okay, so now when you have to draw the full, look at the problem first. You see the support is at two ends B and D. We have to draw the shear force and bending moment diagram for the beam. So therefore if I start from the left end, then I need to find the forces acting at B. I don't need the forces at D because they will come only at the last part, and by then my problem would have been solved. So the reaction at D will just help me to verify my answer. So let's see. So we need to find, so first step be to find By. So let's draw the full free body diagram of the beam. We have 20 kilonewton, we have 40 kilonewtons, and then there is By, and then we have Dy. And each of these distance is 2, this distance is also 2, this distance is also 2. So to find By, well, what I'll do is I'll directly take a simple equation, take sum of moments about D is equal to 0. When I take sum of moments about D is equal to 0, I will get 20 multiplied by 6. This is in this direction. So this is what I'm considering the counterclockwise direction is positive. Then we will have minus By multiplied by 4 plus 40 multiplied by 2 is equal to 0. And I take some moments about D is equal to 0, that will give me 120 plus 80 is equal to 4 By, and so By is equal to 50 kilonewtons. And actually if By is 50, you can easily work out Dy will be 10 kilonewtons. So I don't need this, but then I can also get Dy is equal to 10 kilonewtons. This comes from sigma Fy is equal to 0. So now let us look at our total beam. Let me just draw the loading diagram. This is what one does. Let's draw the loading diagram. So we have, I'll use 3 and 3, 6 and 3, 9. So this is 2, this is 2. So I have 20 kilonewton force acting like this. I have 50 kilonewtons acting at B. So this is A, this is B. Then I have 40 kilonewtons here and I have 10 kilonewtons here. This is the total loading for the beam. I'm taking a very simple example first. We will talk of distributed forces after this. So now we have to draw the shear force diagram and the bending moment diagram. So this is, we start from this axis. This is for shear force. This is for bending moment. So this is from 0 to 6. Now, if we start when x, so we are taking x, we are going from the left section when x lies between 0 and 2. So notionally in your mind, you will be cutting a section here. X is the place where you have cut the section. X lies between 0 and 2. Now we start to see. On the left, when I am cutting a section at X, the free body diagram which comes is basically 20 kilonewtons and then I have this section X. So what is the shear force? Let us look at rule A. A downward force P creates on all sections to its right a shear force equal to minus P. So this is minus 20. So the shear force here then becomes equal to minus 20. And till I reach 2, the shear force states to be minus 20. So this is minus 20 in shear force up till the point B. So this is A. Till I reach B, I will get only minus 20. What happens at B? At B, I have an additional force of plus 50 kilonewtons. So what will happen in the shear force diagram? In the shear force diagram, I will get a jump of 50 kilonewtons. So I was at minus 20. To that, when I add 50, what will I get? The value becomes 30. So therefore, in the shear force diagram, I will reach at the point B. The shear force will become 30 and it will continue to be 30 till I reach the point C. Because now, so that means when 0 is less than x is less than 2, V is equal to minus 20. When x is between 2 and 4, then V is equal to minus 20 plus 50 is equal to plus 30. And now, can you tell me what will happen when I cross C? When I cross C, what should I add to 50? I should add minus 40. So therefore, I will add minus 40 because this is minus 40 force. So when I add minus 40, I will come down to minus 10. And then I continue till minus 10 till I come to the point D, and that is what the shear force diagram looks like. So the shear force diagram is minus 20 here, its value is plus 30 and this is minus 10. So this is the shear force diagram for this beam. Let us look at the bending moment diagram. In the bending moment diagram, when I cut a section X here, this force is 20. Now what is zeta? The distance between the cut section and the pointing of 20 here is, so when we have, so let me give the explanation and I'll draw the diagram later. So when 0 is less than x is less than 2, the bending moment is equal to minus 20x. So that means at x is equal to 2, the value is equal to minus 40. So we are starting from 0, at x is equal to 2, we reach a value of minus 40. So this is how the bending moment diagram looks like from 0 to 2. Now when I go from 2 to 4, so now let me draw the figure again. This is 20, this is 50 and my section is somewhere here. this is x, and this distance is 2. So now when I write the expression for the bending moment, because of 20, what will be the contribution? It is downward 20. The distance between the cut section and 20 is x. So it will be minus 20x. Now, what is the contribution of 50? Because now in this second part, an extra portion of 50 has come. What is the contribution of 50? First of all, 50 is positive. So I'll have plus 50 times the distance between the cut section and 50. Now this total distance is x. This distance is 2. So it will become plus 50 times x minus 2. And this is what will continue in the bending moment diagram till we reach a value of 4. So when I put x is equal to 4, what answer do I get? I will get m is equal to minus 80 plus 50 times 4 minus 2, that is 100. So m is equal to 20. That means from minus 40 till this point C, I will go to a value of plus 20. This is a straight line. So the bending moment diagram, I will get a straight line from here to 20. Is this clear? This is what happens from 2 to 4. Now let us see what happens to the bending moment diagram when x is between 4 and 6. Now when I look at it, when I draw the cut section, you need not draw the cut section always. I am just doing it to explain that on this I have 20, I have 50 and I have 40. And this is my cut section x now. This distance is 2, this distance is 2 and the total distance is x. So now the bending moment diagram, we start from 20, so it will become minus 20 times x plus 50 times x minus 2, and now we have to add the contribution of 40. What is the contribution of 40? Minus 40 times the distance between the cut section and 40, where 40 is acting, so it becomes x minus 4. And so this is the expression. You can simplify this. This will give you the expression for the bending moment, and you will realize at x is equal to 6, bending moment m will become equal to 0. Put in the value 6. Why does it become 0? Because there is a pin end. At this end there is no moment. So therefore in the bending moment diagram I will move from 20 to 0 at the point D. So this is A, this is B, this is C, this is D. So this is what I have for the bending moment diagram and the shear force diagram, and that is how I draw these diagrams. Even these equations which I wrote to you, or when I wrote these equations, this was to explain things to you. Otherwise, just by looking at the loading, you could have directly, using the rules which I wrote, you could have drawn these shear force and bending moment diagrams. Of course, you need to write these equations to calculate the values at the end points. This just gives you the shape, and that is how we get to the shear force and bending moment diagrams when we had only point forces. Now, what will happen, and this is what I will leave you with some thoughts. We had this simple case like this. Now, what we see is some things to observe. A concentrated or a point force causes a jump or a step in the shear force diagram. We had a force of 50 kilonewtons acting at point B. If I look at shear force diagram at point B, there is a jump. In fact, if I have to use a word causes a jump or a step, the correct mathematical word for this will be discontinuity. That means to a section just before B, just before x is less than minus 2, the shear force is minus 20. And at a section just after B, the shear force is plus 30. Now, if you ask me what is the shear force at the point B, I don't think I can define that. Why? Because there is a discontinuity in the shear force at the point B. I cannot define a unique shear force at point B. I can define a unique shear force up till point B, and I can define a unique shear force after point B. At point B, shear force experiences a discontinuity. And this is what we will find is that whenever there is a concentrated force acting at a point, there the shear force diagram will experience a discontinuity, and you'll see a sudden jump or a drop in the value of shear force diagram as at point B and at point C. And we notice in the bending moment diagram, because of the point force, there is no jump. The slope changes. There's a way in which the slope is changing, but the discontinuity is not there in the bending moment diagram as it is there in the shear force diagram. So, when do we get a discontinuity in the bending moment diagram? In a bending moment diagram, if there is a concentrated moment or couple at a point, this will cause a jump or discontinuity in the bending moment diagram. And this concentrated moment will do nothing for the shear force. Now, the girl from CE Pune had asked a question about the concentrated moment, and let me give you an example where the location of concentrated moment becomes important. Suppose I have a beam AB like this, and on this beam there is an L-shaped protrusion, and on this extended part a force F1 acts. Now if I have to draw shear force diagram and bending moment diagram of the beam AB, what will I do? How do I draw the shear force diagram and the bending moment diagram of the beam AB? What I will do is, at the point C of the beam, where the L intersects the beam, we find the equivalent force system due to F1. Now if you realize, look at our first lectures, what is the equivalent force system due to F1 at point C? The equivalent force system at F1 due to point C will consist of two parts, a force F1 and a couple which is equal to, if this point is D, CD cross F1. So what I will get is a couple M1 here which is equal to CD cross F1. And this couple now is a concentrated couple which acts at point C as far as the beam AB goes. So now when I draw the shear force and bending moment diagram of AB, and if I cut a section before point C, I will not get the effect of M1 in the shear force diagram directly. The effect of M1 will come through the support reaction at A. But in the shear force diagram of the beam AB at the point C, I will get a jump because of force F1, and in the bending moment diagram also I will get a jump because of the point moment M1 acting at point C. So in all points before C, effect of M1 will not come directly, and the effect of M1 will come after the point C. So this is what will happen in this. So in the next class we will continue. We will do distributed loads. We will see more complex problems on shear force and bending moment. Thank you.